In the last class, we looked at the CMOS inverter. And we found that at some magic voltage Vx star, both the transistors M1 and M2 are in saturation, and you get in theory you get infinite gain if since the lambda of the transistors is 0. In practice, because the channel length modulation factor is non-zero, you will get some finite gain, but the hope is that the gain is large. So, if you plot Vx versus Vy, you get a characteristic like this, right. So, this is VDD, this is VDD, and this is some large slope, and that value is the magic voltage Vx star. And this lower limit of swing on the at the node Y to keep both the transistors in the saturation region is Vx star minus Vtn, right, and on the positive side it is Vx star plus Vt. Okay. And so, the next question is the following. Let us say you are in a lab and the symbol for the CMOS inverter, of course, you all know, it is drawn like this. It does not mean that there is no other terminals. I mean the fact that there is a supply and a ground are understood, right, and are simply not shown to avoid clutter in the diagram. So, let us say you are in a lab, right, and you basically need to find the magic voltage Vx star, right. So, what will we do? How will we go about it? Okay. Measure Vy, okay. 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 So, one one way to do it is basically say well, we know that Vx is the point at which the characteristic has a very sharp slope. So, if you plot Vx versus Vy, right, then and obviously you look at the characteristic and tell me why, you can tell us what we can tell you what the value of Vx star is, right. If you do not want to plot the characteristic explicitly, do you think there is any other way of finding the finding this magic voltage? I mean, I hope you understand the question. The question, the answer, one answer is that he says, well, what is there? You plot the characteristic, you look at the characteristic, you tell what that Vx star is, correct? And the question I am asking you is there another way of doing this without actually having to plot out the entire characteristic and then find what that Vx star is? But you are in a lab, I mean, what current equation? Okay. That is what he is saying, no? No, finding the derivative of the output characteristic is like saying first I find the output characteristic, then I differentiate it, right, which seems even more complicated than finding the characteristic itself. Yeah, well, so one way to think about it is that if the input, let us say we have some voltage, we put some arbitrary voltage Vx, okay, and if the voltage Vx is less than Vx star, what do we expect Vy to be? We expect it to be very high, right, because we are somewhere somewhere here. Okay. When then what do you know? I mean, so then so if you put in some arbitrary voltage and you find that the output voltage is too high, right? If it's a VDD, then you know that the input voltage is less than Vx star. If you put in a voltage which is greater than Vx star, what do we find? The output voltage is too low, right? So what is so what should you do then? So if Vx is less than Vx star, Vy is too much, and therefore what must you do? Must increase Vx, right? On the other hand, if Vx is greater than Vx star, Vx is too, Vy is too small, and we must therefore reduce Vx. Does it make sense? Right? So if the output is too high, we must increase Vx. If the output is too low, we must decrease Vx. So what do you think we should do? One way to do it is to simply connect nodes X and Y together. Okay, all right. But when you do something like this, you must also make sure that the quiescent points of the transistors are not disturbed in any way, right? In other words, what do you call, if the node X draws current, right, then the node Y will get, the potential of node Y will get disturbed, right? But in this particular case, what comment can we make about the current drawn there? It is 0, right? So connecting Y to X is not going to rob any current from node Y, right? And as it stands, we see that if Vx is equal to Vy, then which is equal to Vx star, then both the transistors are indeed operating in saturation. All right. So this is a this is a common, this is a clean way of finding that Vx star. Okay. And so one way of making an amplifier therefore is basically, if you have identical inverters, which is possible on a chip. So one way is to get the magic voltage Vx star. Now if you want to make an amplifier with a large incremental gain, what do? We know how to find the Vx star. So what do? If you want to make the equivalent of a common source amplifier, what do? Where do we want to apply this? I mean, so we need to bias this inverter at the right place. What is the right place? Gate. Okay. At what voltage would we want to Vx star? Okay. And then on top of it, you must add a small signal. Okay. So we know how to find Vx star. So now how do we make the amplifier? Very good. So basically you say, okay, if we take another inverter, okay, the voltage here, the total voltage here must be Vx star plus small vi. So the question is, how do we generate this Vx star plus small vi? Any suggestions? Okay, so one suggestion is to say, hey, well, why not do this? This is our inverter, and why don't we simply connect it here and connect it how? What do I do? Kick. What? Okay. So, let us say we have Vi here and some source resistance Rs. What do I do? Okay. Okay. Alright. So, what is the incremental voltage there? Please let us think through this. What do? We simply replace every transistor with its incremental equivalent. So, let us do that. So, what is the incremental equivalent of this inverter when the output and input are shorted? So, the NMOS transistor in the inverter is GMN times let us call this small Vx, alright. This is GMP times Vx, okay. This is Vx, alright. Sorry, the gate and the drain are connected to each other, alright. Then capacitor is a short circuit, this is Vi, this is Rs, and if you have output resistance, I mean this is RON parallel, ROP, this is Rs, then you have this is small Vx anyway, this is GMN plus times Vx, this is RON parallel RO. Okay. So, what is the incremental voltage Vx? How does this look, by the way? Yeah. So, you apply voltage Vx here, you are drawing a current GMP times Vx there and GMN times Vx. So, it is equivalent to having two resistors, 1 over GMP and 1 over GMN, which they are all in parallel. So, basically you can think of this as a resistance which is 1 over GMN plus GMP. Is this clear? So, what comment can you make about small Vx therefore? There is voltage division. So, if you neglect this RON parallel ROP, then the voltage there small Vx is nothing but Vi times 1 over GMN plus GMP divided by 1 over GMN plus GMP plus Rs. That makes sense? And then the output voltage will be this multiplied by times minus GMN plus GMP times RON parallel ROP. Does that make sense, people? Now, the question is what happens with so obviously if gain is large, then this GMN plus GMP is going to be I mean you would hope that this GMN plus GMP is a large number. Now, therefore, what comment can you make about this quantity? Okay. So, the question is this even correct? We did this before in another context when we do you see the relationship to what we have seen earlier when we did the common source amplifier? Remember, we found a way to bias the transistor in a way such that the current is independent of threshold voltage and all that. What did we do? We used a current mirror, right? Okay, how did we connect it to the common to the gate of the transistor? Now, why did we put the resistor here? To make that voltage independent of, yeah. So, okay, so now does that ring a bell? What is the difference between this and this? Is it, do you see an analogy at least? Yes. So, what should we do? So, what we therefore need to do is put a large resistor Rx here, so that in the incremental diagram what happens? You get to put a large Rx here, so that this becomes plus Rx, and if Rx is chosen to be much larger than Rs, this is approximately Vi. All right. Okay. I mean, this is exactly analogous to what we did earlier. I hope you are able to see the connection. Now, if we want, for example, to get a large gain without using an additional inverter, right? Any suggestions? We want to be able to use the input source right and connect it to the inverter, but we want to not be able to use, let us say we are not able to afford another inverter, right. We have done this before again, if you go and think back to your common source amplifier days, right. One way was to use an additional transistor and a mirror like what we have done here, right. Is there a way of not using this additional transistor? There what did we do? We connected gate to drain through a what resistance? Was that a small resistance or a large resistance? Very large resistance. So, basically the same thing works here too, right. So, as far as quiescent much larger than for example, let us say RL, then what happens? What for the operating point, what comment can we make? So, what is this voltage? Quiescent, what is the quiescent voltage there? Vx star. And what comment can you make about the quiescent voltage drop across Rx? Is going to be 0, right, and that is because the gate does not draw any current. Okay. So, you can see that is very analogous to what we did with the common source amplifier. Okay. Okay. So, with that the biasing of the CMOS inverter is that discussion is complete. I mean, but there is so many interesting things you can do with CMOS inverters. For example, let us assume this Rx is very large. Okay, can somebody look at this and tell me what the incremental output voltage is?
The second stage will get parallel with the first stage. So if second stage
It's identical. Two identical inverters are there.
the gain will increase, will get double.
Let's assume that ROP and RON are both infinite. Small signal equivalent. Okay, so Rx is very large. Rx tends to infinity. So in the small signal, it doesn't appear. So this is Vi. What is the small signal equivalent to the CMOS inverter? It's operating. What is the quiescent voltage here? Vx star. What is the quiescent voltage there? Vx star. All right. So what is the incremental equivalent of this guy there?
Gate of the first
And
at drain GMP and another called GMN also.
So GMN plus GMP times Vi. Okay.
Gate of the gate and drain of the second stage is also shorted. So for that it also current source is same.
So this will be GMN plus GMP times V0. Okay. All right. Is this clear? Remember that the drain and the gate of the second inverter are shorted. So therefore, that is VO. Is this clear, people? So now what does that guy look like? The voltage across that current source is V0. The current is GMN plus GMP times V0. So this is nothing but a resistor of value 1 over GMN plus GMP. All right. So now what is the output voltage? So this VO must be therefore equal to minus Vi. Okay. All right. Now if I take a third identical inverter, now I want to ask you, all the inverters identical. What is VO? Quick. This can't be taking that long. Minus 2. Okay. If instead of 2 inverters here, I had 10 inverters in parallel, right? Okay.